Okay, you guys, hi, welcome. Today what we're going to do is we're going to be talking about the differences in means. All right, we're going to go through the same process. Section 10.2 is just like section 10.1. First, we're going to talk about the difference of the sampling distributions. Then we're going to jump into the intervals. Then we're going to jump into the actual hypothesis test. All right, so your sampling distribution, same concept as from chapter, was it 8? I think it was chapter 8 a while ago. But same concept as that. No, actually, I think it was 7. When you're going through these, sorry, it's one of those two. Your sampling distribution, if you've got population 1 and population 2, mean 1, mean 2, and you both have both your simple random samples, we know that it's approximately normal if both sample sizes are large, meaning they're both greater than 30, or if one is normally distributed and the other is large. We can still be using the idea that the mean of the sampling distribution is the two population means subtracted from each other. We can still be using the standard deviation of your sampling distribution is going to be the standard deviations, where it's standard deviation 1 squared over n1 plus standard deviation 2 squared over n2. So the same idea as when we had proportions, right? And we had a fraction for sample 1, fraction for sample 2. We're going to have the same idea here. We're just now switching over to standard deviations. This can be used as long as the 10% condition is met. All right. So if we have example 1, a fast food restaurant uses an automated filling machine to pour soft drinks. The machine has different settings for small, medium, and large drinks. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution, mean 27 ounces, standard deviation 8. When the medium is setting, then M is going to be normal distribution 17 ounces, standard deviation of 0.5. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled using the large setting and 25 cups filled using the medium setting. So we're going to do the differences. Again, this is not a paired t-test. This is do all the larges, average them up, do all the small, mediums, average them up. Okay, that concept. If we have a sampling distribution though, all right, we want to let that be the difference in means of the sample amount. The shape of our sampling distribution is going to be normal. And we know that because we were told that both population distributions are normal. If you know they're both normal, then you're going to have that the sampling distribution is normal. If they're not both normal, that's when your sample size comes into play. To find your mean in of your sampling distribution, it's going to be large minus small, right? The mean of large minus the mean of the medium, and you would get 10 ounces. If we want to calculate and interpret your standard deviation, okay, you're going to do, it's the standard deviation for the sample mean of larges and sample means of mediums. So it's a largest standard deviation squared over 20 plus medium standard deviation squared over 25, because they were the two sample sizes in the second to last sentence of the problem. So we get 0.205 ounces is going to be the standard deviation of the difference. So when you interpret it, okay, we can go back to that same concept of what it means to interpret. It's going to be the difference, large minus medium, in the sample mean amounts of liquid typically vary by about 0.2 or 0.205 ounces from the true difference in means of 10 ounces. Okay, because again, we're testing that it was 10 ounces. So that's that. This isn't asked very often. This is something that can pop up, just like with proportions. This is something that can pop up, but doesn't pop up all the time. The next couple things are huge. All right, now, I know that when you look at this formula, you're like, oh my goodness, that is a lot of symbols going on. It doesn't need to be an interval notation. All right, so that's the first thing, is you could think of it like we keep writing it as plus or minus. So it could be x bar 1 minus x bar 2. Plus or minus your t star, and then square root of s1 squared over n1 plus s2 squared over n2. All right, so you could also look at it like this plus minus notation that we keep using. The plus minus is right in front of the t star, okay? This standard deviation is the same standard deviation we just learned, all right? One of the big deals is that when your degrees of freedom are equal, you're going to use the small, or if they aren't equal, right, you're going to use the smaller the smaller degrees of freedom. So like on that last problem where you had n is 20 and n is 25, you're going to use the smaller. So you would use the smaller n, which is 20, and do the degrees of freedom for that, which was 19. So whatever notes you need to take to remind yourself of that, I would do that. Okay. When we're going to look at our conditions, all right, our conditions we're going to have, did they come from random? All right. Did we have, and remember it's both samples were randomly selected. Do we have our population is at least 10 times our sample size for both samples? And then you've got to be careful, right? If you have for each sample, the corresponding population distribution is normal or your sample size is large enough, right? If you have unknown shape and n is less than 30, you need to do a little sketch, okay? They're going to show no skewness or outliers, just like we've done for every other t-test, okay? But now you're just checking both data sets, all right? So if we take a look at this guy, let's talk about chocolate chip cookies, which are my favorite, all right? Ashton and Olivia, actually that's different. My aunt makes really good cookies too that are not chocolate chips, but Ashton and Olivia wanted to know if generic chocolate chip cookies have as many chocolate chips as name brand chocolate chip cookies on average. To investigate, they randomly selected 10 bags of Chips Ahoy cookies, 10 bags of Great Value cookies. They randomly selected one cookie from each bag. Then they carefully broke apart each cookie and counted the number of chocolate chips in each. So here were their results. So Chips Ahoy, here we go. Great Value, here we go. All right, we want to set up and construct and interpret a 99% confidence interval for the difference in the mean number of chocolate chips in Chips Ahoy and Great Value cookies. So I started by stating my parameters. Let mu1 equal the true mean number of chips in Chips Ahoy. And then we're going to let mu2 equal the true mean number of chocolate chips in Great Value cookies. All right, you'll see up here, I already wrote that my degrees of freedom are going to be 9. Since they're the same sample size, it doesn't matter, right? That both degrees of freedom would be 9. 99% confidence, I just jotted it down while I was doing my work. I got 3.250. Okay, all of this came from one variable statistics, right? You throw this in a list, get your info. Throw this in a list, get your info. We're going to have our hypotheses. Are they equal or are they not? Again, you could also do mu1 minus mu2 equals 0. Mu1 minus mu2 doesn't equal 0. That's perfectly acceptable as well. Our assumptions, we were told that they were right. So we have 2 random samples. They randomly picked 10 bags and then randomly picked a cookie out of each of those bags. So that should be good to go. Our population of all Chips Ahoy cookies, right? So we should include the word cookies. It's going to be at least 100 cookies. Good. Great Value cookies. Yes, at least 100 cookies. Dot plots. I accidentally forgot to sketch this when I was writing out my key. Sorry. So you're going to sketch your 2 dot plots. Okay. You're going to confirm that there's no skewness or outliers, which means you're okay to use T-star, right? Really, you should do this step when you put these in your calculator and then just grab it from there, right? Because that's nice and quick. Or you could grab them by hand. I apologize. I meant to do that and forgot. Sorry. So, interval, all right? Our name is a 2-sample T interval for the difference in means. Okay, formula, x bar 1 minus x bar 2 plus or minus T star, big square root, standard deviation squared over n plus standard deviation squared over n. All right, throw those in your calculator and you get this. When you're interpreting your interval, that's the one where it's how confident we are. So your interpretation would be we are 99% confident that the interval from negative 5.13 to 3.13 captures the true mean difference in the number of chocolate chips in the 2 branches or brands of cookies. The next question, does your interval provide convincing evidence that there is a difference? That's the one where we have to look at the number 0. Because remember, if you have null hypothesis mu1 equals mu2 and alternate hypothesis mu1 doesn't equal mu2, then this is the equal 0, this is the doesn't equal 0. So if 0 is contained, then that means, you should have this memorized by now, do not reject the null hypothesis. Okay, so we would describe it as do not reject the null hypothesis. Because the interval includes 0, there is not convincing evidence that there is a difference in the mean number of chocolate chips in the two brands. They were too close. Even though they were different, they weren't a big enough difference to be statistically significant. All right, now off to our hypothesis test. All right, when you're working on these, you're going to have this as your huge test statistic. This actually just becomes 0 because it's going to be, we're hypothesizing they're equal to each other, so you don't need to worry about this. Okay, we're just going to do x bar 1 minus x bar 2 over the standard deviation that we just had. Okay, same idea. Your degrees of freedom are going to be equal or smaller to, like, it's going to be, if they're equal, like, I mean, sorry, I read that out loud wrong. Where your degrees of freedom are equal to the smaller of which degrees of freedom it would be. You know, so pick your smaller n and go from there. Same conditions. Okay, so we have the same conditions that we're working on that we just had. And then we take a look here. Okay, so this problem, and if you need to pause, you can pause. We're talking, and to read it yourself, we're talking about whether you take calcium supplement or you take a placebo, and then we're looking at blood pressure, okay, and if it's going to help. So I put group 1 is your calcium, group 2 is your placebo, because it was listed right here at the end of the sentence. All right, again, not a paired t-test. It's average up all your group 1s, average up all your group 2s, okay? It's not a before-after scenario. That's a paired t-test. It's fine that your sample sizes are different. That's very okay, all right? So it's saying, is this outcome good evidence that calcium decreases blood pressure in the entire population more than a placebo does? All right? So we would have parameter, let mu1 equal the true mean decrease in blood pressure for men taking calcium. Mu2, true mean decrease in blood pressure for men taking the placebo. If it's going to be better, that means you're going to have a greater decrease. So if your decrease is higher, that's a good thing, okay? So our decrease is right here, okay? So it's going to be like calcium is greater than the placebo, okay? That it's going to be a higher number for the decrease, okay? We're going to have a randomized experiment, so we don't need to worry about, like, the randomization was in the experiment part. It wasn't a randomly collected sample. 10% condition, we didn't need to check this time because it wasn't a sample without replacement. Hey, look, I remember to draw my two dot plots. We have no skewness or outliers, so it's okay for us to proceed with t-star. Our name is a 2-sample t-test for the mean. Our formula, you had to do your 1-variable statistics for both pieces of information. Okay, calcium, the average decrease was 5. Placebo, the average decrease was actually negative 0.273, which actually means that on average their blood pressure got worse. It didn't increase. It got poorer. Okay, it didn't decrease, so it actually increased. You're going to have x, like x bar 1 minus x bar 2. Be careful, minus and negative is really addition, okay? Then you do your square root. This is calcium. This is the placebo. Okay, we got 1.604. When you find your p-value, all right, you're going to use, this is a right-tailed test because our alternate hypothesis was a greater than value. I put a little star. Be sure to use the smaller. So since 10 is the smaller sample size, that means 9 is the degrees of freedom we want. We're going to have TCDF, right-tailed test, so 1.604 to infinity, degrees of freedom 9. Here's our p-value. Same deal as with every other thing. If it's a 2-tailed test, you have to double that p-value. Okay? So then I came over here. I compared my p-value to alpha. P-value is greater than alpha, which means do not reject the null. So our summary is we cannot conclude that the mean blood pressure decrease of those taking calcium is greater than those taking the placebo. Right? Even though it was different, it wasn't a big enough gap between the two to be statistically significant. So what I'd like you guys to do is I'd like you to now try this problem on your own. Okay, we're talking about balloons and if they decrease, you know, helium versus regular air. And if they, if we're looking to see, do helium-filled balloons deflate faster than air-filled balloons? I'm getting the vibe that a lot of people haven't perhaps necessarily been doing as much practice as they should until the very absolute last minute, which is not where we want to be. So I'd like to request that right now you guys like pause the video, all right? Practice this on your own. Like if you want, you can do it in pencil, but try this problem based on how many hypothesis tests we've done, okay? And you just wrote beautiful notes for problem number 3. Hopefully you can do this, all right? And then I'm going to, so you're going to pause, do the problem, and then I'm going to unpause now, all right? I'm going to show you my answers. Okay. So there's the beginning. And if you have questions and you want to go through them in class, I will happily go through questions. You know that I love to go over stuff and make sure you totally understand. But I can't do it all for you, right? You got to be able to do it yourself. That's the important part. That's showing your understanding. You might have freaked out that you had such a big value. That's okay. These are ridiculously different with incredibly small standard deviations. All right. So I put 0. I forget what the scientific notation was. So maybe I should put essentially 0. Okay, with an approximate. Don't worry about this. Reject the null hypothesis. Make your conclusion. And then hopefully you also interpreted your p-value. You have all of this. If you have questions, I would love to go through it with you. Okay, so good job today, taking great notes. I'll come back up here if you need to look at this again. You can always pause, but like you shouldn't be copying off of this because you did this on your own and you're just erasing and making little tweaks of things that you got wrong. Okay, sound good? All right, I'll talk to you soon.